talked about the idea of work, right, which tells us how much energy is transferred by an interaction. We've talked about the idea of power, right? Power tells us what the rate of energy transfer is, right? And in order to transfer energy via work, you need a force, and you also need a velocity, right? The object actually needs to be moving in a way that is parallel with the force. In this video, I instead want to concentrate not on transfer, but instead on storage, right? So we've so far been talking about transfer. We now have to ask the question, where is energy stored? And as I said earlier, there are two places energy can be stored. One is in kinetic energy, and one is in potential energy. And notationally, I'll sort of interchangeably talk about T or KE as being kinetic energy and V or PE as being potential energy. So we're going to concentrate on kinetic energy in this video. In general, the kinetic energy of a particle depends on how fast the particle is moving. And in particular, it's 1/2 the mass of the particle times the velocity of the particle squared. If I have a bunch of particles, right, I could actually talk about what the kinetic energy of a system is, right? The kinetic energy of the system is simply the sum over all the particles in the system of their kinetic energies. One thing you'll note about both of these quantities is that they are one scalar quantities, right? Remember that energy is a scalar quantity. You can see pretty easily what the units are: kilograms times meters squared per second squared, or kilograms meters per second squared times meters, which is the same thing as force times distance, so joules. And the third thing that you'll note about kinetic energy that's kind of an interesting aspect of it is kinetic energy is always greater than 0, right? Because velocity is always greater than 0, or velocity squared is always greater than 0. Velocity can be, is a vector, it can be in different directions, but when you square the velocity or take the dot product of the velocity with itself, it's always greater than 0. So these two expressions alone are in principle enough to figure out what the kinetic energy of any system is, but it's often handy when you're talking about systems that are both translating and rotating. So let's return to our friend the Caber toss. So I've got this Caber that's rotating, but is also translating. I could actually take this system and say, okay, I'm going to break this system up and do a bunch of little chunks. Right? When I break it up into these little chunks, I'm going to ask the question, how fast is each little chunk moving? I'm going to square that velocity that chunk is moving at, multiply it times its mass times 1/2, and I'm going to add them all up, and that will tell me what the kinetic energy of the system is. I certainly can do that, and in fact, you could think about how you might do that, right? I could say, okay, this is the position vector to the center mass, and I'm going to think about what these vectors are that go to different points on the object, and so on. But it's actually, when you do that, what you actually get to is something that is not a very surprising result if you think about the different ways that we've been talking about abstracting, rotating, and translating motion. It turns out that the kinetic energy actually consists of a translational component plus a rotational component. And this translational component is basically the sort of particle abstraction of this motion, right? It's 1/2 of the total mass of the system times the velocity of the center of mass squared, right? So if you imagine taking this whole system and compressing it to be a point mass that's located at the center of mass, the kinetic energy of that would be 1/2 mv squared. And then there is a component that has to do with the idea that the system is rotating about its center of mass. And that rotation about the center of mass gives me some additional kinetic energy, which is 1/2 the moment of inertia times the angular velocity about the center of mass squared. Okay? So these two things together tell me what the kinetic energy is for a rotating and translating object. So just like you can break angular momentum into a translational component and a rotational component, you can also break kinetic energy into a rotational component and a translational component. The last thing I'll notice about kinetic energy is that like linear momentum, kinetic energy depends on your choice of coordinate system, and in particular depends on what the relative velocity of your coordinate system is, right? Kinetic energy doesn't depend on whether I choose my origin to be here or here or here, but it does depend on whether I choose an origin that's stationary or an origin that's moving with some other relative, with some velocity relative to this origin, right? And all three of these could be inertial reference frames so long as that velocity is constant. So big ideas here. Kinetic energy has to do with what the mass is times the velocity squared. It's a scalar quantity with units of joules. And when you talk about the kinetic energy of a system, you can always break the system down into a bunch of little chunks and ask about the kinetic energy of each chunk. But for a rotating rigid body, you can also take that expression and manipulate it to be able to break the system down into a part that has to do with kinetic energy of the sort of center of mass, so the sort of particle part of the kinetic energy, plus a part that has to do with the rotation about the center of mass. And you can see this sort of nice analogy here between mass being analogous to moment of inertia and velocity being analogous to angular velocity.